Okay, physical science time. Today we're talking about atoms and their structure. Be quiet, please. Atoms and their structure. The word atom comes from the Greek a, what's the Greek prefix a mean? Almost always when we encounter it. Yeah, what's it mean?
Alpha.
No, this is the Greek letter alpha. Like if you talk about asexual reproduction, that's reproduction without sex. Without sex. Reproduction without sex is asexual. So what's the prefix a mean?
No.
Yeah, none. Not, you can't have it. Can't, not, no, those things. And then no tums. Yeah, where we run out of tums, that's atoms. No. It's the next letter, or the next little, kind of is weird, but is tomos, which means it's the same. You haven't taken med terms, but you will someday, probably, many of you. But the Greek root tomos means, so this is without, and this means to cut. So if you have like a, I'm trying to think of an example that doesn't have to do with childbirth. Okay, if you have the T in CT scan, the C stands for computerized, and the T stands for tomography, which is, it means literally writing to cut. But what it does is they take little like snapshots of different slices of your body. When you get a CT scan, they take slices of your body. They use x-rays to take different slices of your body. So this is you laying in the CT scan bed, and the CT scan does not literally slice you, but it takes an x-ray of here, and then it takes an x-ray of here, and it takes an x-ray of here, and it does that so you get a three-dimensional picture of what your brain looks like or whatever. Does that make sense? So these are slices, they're cuts. So a tomos, an atom, is without cut. What does that probably refer to? Why might we use this word to describe those tiniest little particles? Without. Yeah, so they, what? Yeah, so they're supposed to be, they are the indivisible, I wrote the letter U, indivisible particles. We know now that they can be divided. This word was named in the 300s, the 3rd century BCE. It was named 300 years before Christ walked the earth. And so it was named that, but it wasn't actually used scientifically until the late 17 and early 1800s. But even then, we didn't know that they could be cut. And so we just named them indivisible particles, atoms, after what this Greek philosopher Democritus had named them in the 3rd century BCE. Yes?
So in like the vacuum of space, is there any particles? Or is it
There are particles in the vacuum of space. Not nearly as many, but there's no true vacuum. I mean, you could probably find an area, maybe even an area this size, that had absolutely nothing in space. But usually there's somewhere, I can't remember the exact numbers, but somewhere between 10 and 1,000 atoms per cubic meter in outer space. So you remember here's our meter stick again. This would be a cubic meter. This width, this times this. So this is a big area with something like thousands of atoms in it, which is not very many at all. Anyway.
milk have atoms in it?
Milk does have atoms in it. I appreciate the very normal and reasonable question that you guys are asking. Okay, so what is an atom then? When you did your bell work and it says diagram an atom from your current understanding, tell me what to put on the board from your understanding. What should I put here? And do we all agree?
You should draw a nucleus with protons.
Okay, a nucleus. What's the nucleus mean? Where is it? Where am I going to draw this relative to everything else in the drawing? In the middle. Okay, yeah. So we have a little nucleus here. And what's inside of here?
Protons.
Yeah, this is a nucleus, and we should draw this, because your drawing might be wrong, and even if it's not, you should draw it again. Nucleus, which contains protons and neutrons. And we'll talk about those in more depth later, obviously. And then, that's it. That's an atom, right? This is an indivisible particle. No. What else is there?
Your electron.
There are electrons. There's an electron cloud, which I'm just going to indicate with a circle with a little baby electron out here. And we're going to call this an electron orbital. And I'm going to put that in quotes, just like I did it with my friends in quotes, because they don't really orbit. We often diagram them as orbits, but what's really happening is what these cowboys just said. It's a cloud. Not a cloud of electrons, but a cloud of where electrons can be, because things are kind of spooky on this level. Let me erase this little guy getting cut up. Speaking of spooky. So we have here an atom, a very, very basic drawing of an atom with a nucleus in the middle and an electron orbital around it. Protons and neutrons exist in the nucleus. So let me show you. This is not going to be to scale, but if I have here, these are my balls of science, and this one, we'll say this one is a proton. We'll say this one is a neutron. Neutrons don't always have little tails. Just a ball I had in my desk.
Don't throw it at Chloe.
I probably won't this time, but we'll see. Proton, neutron, and these guys exist in the nucleus. And then this is like the little baby electron, and he is, a lot of times, like on the Jimmy Neutron theme song, is like zooming around it, and that's what we often think about. But what really happens is that on this scale, things are, like I said, spooky, and what really happens is the electron will stop existing here and just start existing here. There was no movement. It just stopped being here, and it started being here. So they're flashing in and out of existence all over the place around the nucleus. But the point is, these are relatively large particles which have what physical property? No, these ones. They do have a, so one of these has a charge, but what do these, both of them have that's a physical property? Yes, they both interact with the gravitational force because they have mass. These are massive particles, write that down. These two particles, the big ones, this is the reason I'm doing this demonstration right now, is because these ones that you can see are bigger than this little guy. These ones we say have mass. What am I implying about the electron? It doesn't. That's not quite true. It has very, 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 very little mass. But we usually say it doesn't have mass because it makes our calculations for what we're going to do today easier. So these two, what do these two have in common? Two things. They both have mass, and they both have a gravity. Yeah, that's true. But I'm talking about also where they are. They both have mass, and they're both inside the nucleus. And this one.
Orbits.
Yeah, it teleports, but it's outside the nucleus, and it has no mass. Okay, so try to remember this little demonstration as you're doing your worksheet and your test, because I really think it'll help you. A lot of times I think the problem that people have when we do the calculations we'll do today is that they forget which ones have mass and which ones don't. So these two big guys in here, we have a neutron and a proton. Let me do them in different colors, so I think that'll be much, much prettier. Let me see if I can find colors that are similar to the ones I was using. So let's say the proton is the tennis ball, and well, black is a color, and the neutron is the racquetball and the pantyhose. Please be quiet. Please be quiet. Please be quiet. No. Okay. So here we have a neutron and a proton, and then the electron, that's kind of a little reddish, bluish marble, so I'm going to say that's red because it'll make it easier to see on the TV. Give me just a second. On the television set. Yeah, I've kind of run out of room here, and it's going to be difficult to see on the video, but just listen to me talk. Okay, so for each of these things, we're going to say where it's located, what its charge is, and what its mass is. They have other properties in this, but without getting into the quantum mechanics, these are the properties we're going to talk about. And we will talk about quantum mechanics a little bit, but without getting too deep into it, these are the things we're going to talk about right now. Neutron, where is it located?
In the middle.
What's that called?
The
nucleus. Proton, where is it located?
In the nucleus as well.
Electron.
Outside the nucleus.
Yeah, we could say outside the nucleus. I'm going to put in the electron cloud. What's the charge of the neutron? I just made this joke right before. Try one more time. Try one more time. It's neutral. That's why it's called a neutron. It has no charge. No charge.
And then the
proton is positive, and the electron is negative. You probably should write this down. You should probably write this down. So the neutron has no or zero charge. The proton has a positive charge, and the electron has a negative charge. And then its mass. The neutron, we say, has a mass of 1 AMU. The unit we use for this is AMU. AMU stands for atomic mass unit. That's it. It's just a unit of the atomic mass. So the neutron has a mass of 1 atomic mass unit. The proton then would probably have a mass of 1 atomic mass unit. And the electron has a mass of, we say, no mass. It actually does. It has a mass about 1/1840th, 1/1840th of these other two. But we usually just round that to 0 for what we're doing today. There are fields of study in physics and electronics that we do talk about the mass of an electron. It's a very important quantity. But for what we're doing today, we're going to say 0. Because what we're doing today is very basic arithmetic with these two numbers. And there's never going to be 1,840, or even if we were going to round it, there's never going to be 920 of these in the same place, because that's half of 1,840, which would make us round it up to 1. So we're never ever going to have any number other than 0 for our mass of electrons for this. Yeah, what's up?
So it's like absolute 0. Is the electron still orbiting?
Yep, the electrons, because it's not, the question was, if it's absolute 0, are the electrons still orbit? And remember, they're really not orbiting, they're teleporting. And if they have any energy at all, even if they have the very least amount of energy they possibly can, which would be absolute 0, they still must change their location.
Is it slower?
I don't actually know. Is it teleporting less frequently? I don't know. I really don't know. Look it up and let me know the answer. I would be happy to know. Okay, so we have, check this out. I was gonna draw my diagram, and I'm gonna instead check this out. What's holding these together? Me. What's holding this in orbit around them? So if I don't, they all fall down, right? Don't pick those up. But in reality, we know that isn't what happens. In fact, the word atom means does not be cut, does not break, does not fall apart. It's indivisible. So what is holding Mr. Proton to Mr. Neutron, and what is holding the electron around them? What is it? What must it be? It's not gravity. In general, it must be, in general, it must be what? Just like I was doing it to them, my model, what in very, very, very basic terms from the beginning of the year? A force. There must be some force. There must be some force here, and there must be some force here. Let's talk about what it is. I'm going to erase this, and I'm going to try to fit what I'm going to talk about into this area up here. Thanks, Doug. Is this not a good drawing?
No, it's a good drawing.
You're really making me nervous. What are the 4 fundamental forces of the universe? We've talked about these once before. Go back in your notes. What are the 4 fundamental forces of the universe? Nope, that's not one of them. And you're just guessing. So please go back in your notes. Maybe someone who's good at taking notes. Gravity's one of them. We're going to put it on the bottom. Why are we going to put it on the bottom? You remember this from the beginning of the year? You should. Okay, there we go. We got strong nuclear. In what order are you saying these?
Oh, yeah. Okay.
He's saying them from strongest to weakest. Strongest to weakest. We talked about this once before, so we're going to go through this fast. What is electromagnetic, weak nuclear, and gravity? And there are 4 fundamental forces of the universe. We talked about these at the beginning of the year. If you need a refresher on what they are in general, you can go back and watch that video. But these are what they are in order from strongest to weakest, and in order from shortest range to longest range. Longest range to shortest range. I'm the other way around, obviously. So what is this force? What's probably the force holding these two things together? This orange one. Well, let me add something else here. Let's say instead of being, this would be an atom of hydrogen 2, which we call deuterium. Let's say instead we have an atom of helium 4. We have an atom of helium 4, which has 2 protons and 2 neutrons and 2 electrons. Do you see why it can't be the electromagnetic force? What's true, if this were the electromagnetic force, what's true of these two? They're alike, so they would
repel.
They would repel. So it can't be the electromagnetic force. But something is holding all of these guys together. The strong nuclear force. The strong nuclear force. The strong nuclear force is the glue that holds the nucleus together. Well, you probably better be paying attention to this. The strong nuclear force is the glue. In fact, we often call the particles that mediate this gluons because they glue them onto each other. We call them gluons. But the strong nuclear force holds these particles in the nucleus together. But it has the shortest range. So if we get a big old nucleus, great big old nucleus with hundreds of protons and neutrons, so let's say we got a big old one with hundreds of neutrons and protons in it. Great big old guy. Since the strong force is the strongest but the shortest range, this little baby over here and this one on this end do not have a very good force holding them together. And so the atom falls apart. And that's why, if you notice on the periodic table, the bigger the atoms get, by the way, this periodic table is arranged from lowest atomic number, which we'll talk about in a second, to highest. So these ones have more particles as we go down here. They're all radioactive because they fall apart on their own. Because the strong nuclear force, while the strongest, is also the shortest range. Okay, so the strong nuclear force holds these boys together. What is the force holding these electrons? Try again. Electromagnetic. Why does that work for this one? What's the charge of the electrons? The charge of the electrons is negative. The charge of the nucleus altogether is positive. And so the electrons are drawn to the nucleus because of the charge change. So the electromagnetic holds the electrons around the nucleus. Where does gravity come in? Gravity only works if there's bunches of these together. Gravity works even, you know what? Even this is made of literally trillions of atoms. It might be billions, but billions or trillions of atoms. This marker is made of billions of atoms. And this marker is made of billions of atoms, right? But you don't notice the gravitational attraction between them because they're too small. Even though they're billions of atoms, they're too small. It takes something like Earth that is orders of magnitude greater, 10 to the 20th atoms, to actually have a noticeable gravitational effect. So gravity has almost zero effect on this scale. These two are what hold the nucleus. So one of them, I'm telling you the dang truth, freshmen always get this wrong in their test. One of the options when it says, what is the force that holds the electrons around the nucleus? People are always saying gravity because they liken this to the solar system. Oh, this is like Earth and this is like the sun. But it is not gravity. It is not gravity. It's the electromagnetic force that holds these together. You had a question. Wait, what is it? Mm-hmm.
I found out that because they have such a high atomic number that they don't even exist in the world for less than
Right. Many of the very, very large atoms don't even really exist for not even a second. So this is what an atom looks like. Let me tell you about. We'll probably have to continue this discussion tomorrow, but that's okay, and we won't have time for a video today, which is also okay. But let me tell you a little bit about erasing. Let's talk about how we can find out how many protons, neutrons, and electrons a particular. I should have probably left this little table down here. But let's look at what we call an isotope. So here we have two. You're not done, are you? Okay, good. Here we have, I'm going to draw two isotopes for you. I'm going to draw two isotopes. Remind me, what's the definition of an isotope?
Iso means by itself.
Okay.
Means
I don't actually know what isotope means, but from your book, what is the definition of an isotope? There you go. Atoms of the same element that have different numbers of neutrons. So I'm going to draw you two isotopes here. Here, first we have. That's one. This is one isotope. This is another isotope. Look at that. We've got two isotopes. How many protons does each have? Number of protons. Try again. How many protons does each have? They each have one proton. They each have one proton. What is this? Yes, Fate. Yep, uranium-235 and uranium-238 are both isotopes of uranium because they have a different number of neutrons, as we'll get to in a second. But the number of protons in both of these is 1. What do we call the number of protons? This is another vocab word. There's another name for the number of protons tells us what else about the atom? Atomic number. Write this down, please. You're going to make a terrible mistake by not writing this down. The atomic number of both of these is 1. They have one proton, so it's atomic number 1. This periodic table is arranged in order of atomic number. What's the atomic number of calcium, which I'm pointing at right now? It's 20. How many protons must calcium have? 20. Zirconium? 40. How many protons must it have? 40. It's arranged by atomic number. The number of protons is what makes it that element. This is what makes it that element. So what makes it zirconium?
That element.
No.
40 protons.
It's 40 protons. What makes it calcium? 20 protons. That's what makes it that element. So what makes it oxygen? It's 8 protons makes it oxygen. What if by a little miracle it gained a proton, which it doesn't normally do? What if oxygen gained a proton? It's not oxygen anymore, it's fluorine. So every atom in the universe that has 8 protons is oxygen, and every oxygen atom in the universe has 8 protons. That is by definition. So the atomic number makes it that element. So what element is this? Hydrogen. This is hydrogen. Uh-oh. What element is this? Nope.
Hydrogen.
It's hydrogen. How many protons does this have? 1. How many protons does this have? 1. So they're both hydrogen. Now what we do is after that we put a hyphen, just like your Fate talked about uranium-235 and uranium-238. We put a hyphen that will tell us the mass number. Hey, remember from this little demonstration I lost them. But what 2 particles have mass in the atom? The proton and the neutron. The proton and the neutron. What's the mass then? If the mass of the proton is 1 and the mass of the electron is 0, what's the mass of this hydrogen? 1. 1. So we call it hydrogen 1. What's the mass of this hydrogen? 2. So this is hydrogen 2. Are these the same element? Yes. Are they the same isotope? No. So isotopes are, it says, atoms of the same element with a different number of neutrons, but it might just as well say atoms of the same element with a different, what's this blue thing here? Atomic mass. Actually, I'm going to call it mass number because I want to be very careful with this. We're going to call it mass number. So if I write something like Fate just said, if I write something like uranium-238, how many protons does this have? No, it does not. How many protons does it have?
Where's it at? 1.
You're looking in the right spot at least. How many protons does it have? Uranium, which is the symbol U.
Where's it at?
Someone will find it. How many protons?
Oh, found it. 92.
92. 92. How many neutrons does it have? Well, this is where we have to do some math. Listen to me. Did anyone hear what I just said? This is where we have to do some math. Because what is its mass?
92.
No, come on. Try to answer it right. What's its mass number?
238.
238. But what has mass? Which 2 things have mass? Protons and neutrons. So if its mass is 238, how do I find out how many neutrons it has?
By subtracting the amount
There we go. Okay, so 238 minus 92 is? Come on, this is not that difficult.
238 minus 92 would be 164. Well, if we took 100 away from 238.
Okay, listen, hey, come on, you cannot be this bad at this. What is 238 listen, let's break it down. What's 238 minus 90? 238 minus 90, that's not that hard. 148. Minus 2 now is? 146. Okay, and now listen, the number of electrons, listen to me, the number of electrons is just the same as the number of protons, unless it has a charge. So what's the number of electrons in this with no charge?
92.
92. This is the math that we do in this chapter. I wish someone gave up writing things down 10 minutes ago, but this was the wrong time to do that, because this is the math, this is what you will have 15 questions on the back that you'll have to be able to do. You need to find the number of protons, neutrons, and electrons for each. And the protons is super easy. How do we find protons? Look at the periodic table and find its atomic number. How do we find number of neutrons? That's where it's tricky. It's the mass number. Where'd my blue go? Neutrons equals mass number minus protons. And then how do I find the number of electrons? Well, it equals the number of protons. That's easy too. The only one people have trouble with is the number. And by the way, where did I get 238 from? If this is my given, where did I get the 238 from? The given. So 92 came from what element it is, and the mass, 238, came from the name, uranium-238. We have enough time to do barely one more. Let's do it together. If I have nitrogen, 15. Protons, quickly. Quickly, protons. 7. Neutrons, this is easier. No, stop. What's number of?
6.
8. It's 15, the mass, minus the number of protons. Electrons?
7.
It's the same number as protons.
It's the same as protons, so it's 7. Okay, we will do a worksheet for that tomorrow. Have a good day.